Hello and welcome to this lecture. This lecture is primarily going to talk about 2 or 3 different ideas, mostly sort of in maximization, minimization, optimization sort of framework in relation to matrices, quadratic forms, matrix norms and other just pure multivariate optimization problems. And it's very surprising how the simple idea of positive operators, eigenvalues, real spectral theorem, all these things play an important role in giving us a sense of the maximization, minimization in these kind of forms. So you'll see it's got lots of interesting applications, and this lecture will walk you through that mainly. So let's get started. So I'll skip the recap for this lecture. I think the previous lecture we were looking at positive operators, which basically are self-adjoint operators which have non-negative eigenvalues, right? So that gives you a sense of what positive operators are. We saw many of their interesting properties. We'll put some of them to use, at least show some applications of them in this lecture, and also applications for the real spectral theorem. I think it's really more applications of the spectral theorem than anything else. I mean, if you look at positive operators, really the spectral theorem is everything in that, right? So the fact that it's self-adjoint and its eigenvalues are non-negative lets you define the square root, and I mean the whole characterization is revolving around that. Okay, so you can think of this as applications of the real spectral theorem. Okay, so the first thing we're going to look at we're going to look at quadratic forms in some detail. These things came up even in the previous lecture. I was in the context of introducing positive operators, right? So we saw how the quadratic forms really, play a crucial role in the definition of positive operators. A quadratic form is non-negative, means the matrix defining that is positive, right? So that's the way we defined it. So now we're going to specialize to real vector spaces. It's not because things are not easy in the complex vector space. It's the same thing, except that just it's easier for me to discuss and present the ideas in real space. So I'll start with the n by n real symmetric matrix, and I'll look at the quadratic form X transpose AX. Okay, so this has a certain form. I don't know if you realized it. I think I didn't really spend some time thinking about it. So in general, if you want to write say x1, x2, xn times a11, a12, a1n, a21, a2n, an1, ann times x1, x2, right? So this is the quadratic form, isn't it? So this quadratic form is basically this. So in case you're wondering why people say quadratic and all that, you'll see it's basically a degree 2 function. So if you look at, if you multiply this out, you're going to get x1, x2, xn, and then you'll get a column vector here. The first entry will be a11 x1 plus a12 x2, like that. So you can do this multiplication first, and then you can multiply by this, right? With x1 you can multiply. Okay, so if you look at it, you will get a11 x1 squared, right, when this multiplies, plus, remember this is symmetric, so a12 and a21 are the same, but for just comfort I'll keep it like this. You will get a12 plus a21 x1 x2, right? So you will actually get a12 x1 x2, and a21 will also give you x2 x1. So I'm just writing it like that. So you'll get terms of this form. Okay, so I'm not going to write everything. So you'll get a term like a22 will be what, x2 squared, right? So you'll get, and generally you will be getting this aij plus aji. Okay, if I is not equal to j, you will get this plus this xi xj, right? So basically you get terms of this form, right? These are degree 2 terms or quadratic terms, right? Xi squared or xi xj, you get terms like that, and then you get a linear combination. So that's why this is called a quadratic form. I didn't quite emphasize this. I thought you could do it yourself, but this is the reason why these kind of forms that are written succinctly, X transpose AX, these are called quadratic forms for that reason. Okay, so you have to keep this expression in mind. So generally quadratic form will be a long series, long polynomial to a multivariate polynomial of it's a homogeneous polynomial. What's homogeneous? Every term has got degree 2, right? So degree 2, this is degree 2, this is degree 2. Every term has degree 2, and it could be x1 squared, x1 x2, x1 x3, like that, and the coefficients are multiplying that and adding it up. So it's a polynomial. So it's a polynomial which is homogeneous, degree 2, right, and coefficients come from the matrix, right, suitably they come. So, this is how this quadratic form looks. Okay. So, if you take small n, you can write explicitly how it will look, right. If you take n equals 2, it will just be, it will have x1 squared, x2 squared and x1, x2, that is it. Okay. And larger n, you will have more and more and more terms. Okay. So, this is how, this is the picture you should have in your mind when you think of a quadratic term, quadratic form. It is a form like this, but it also has this homogeneous degree 2 polynomial expansion in this form. Okay. So, both are okay. If I give you the polynomial, you can go to the matrix, right. How do you go to the matrix given a polynomial, right? You can always go to a symmetric matrix, no? You can take this coefficient, divide by 2, put it in aij and aji, you will get, you can go back to the matrix. Okay. So, this is some basic thing about quadratic polynomials, quadratic forms. I did not quite describe this in the previous lecture, I thought I should do it here. Okay. Hopefully, this is clear. Okay. So, this is how a quadratic form looks. Okay. So, let us move on. So, here is an example. Okay. I have a very simple example for n equals 2, 1, 4, 4, 1. You write out the same expression and add it up, you will get x1 squared plus 8x1 x2 plus x2 squared. Okay. So, now when you think of how to plot this, like for instance, if you want to plot this quadratic form as a function of x1 and x2, it will actually be a 3-dimensional plot, right. And x1 squared plus x2 squared is very easy, right. You can sort of imagine how it will be. But this 8x1 x2 is a little bit confusing. So, in general, in this polynomial, in a quadratic homogeneous polynomial, these cross terms, x1, x2 terms slightly complicate the picture. If it was only, if these cross terms are not there, x1 squared plus x2 squared is considerably simpler than dealing with the cross terms. Okay. So, this is one constant thing about quadratic forms. You like quadratic forms without cross terms better, because you can deal with them easier. It is easy to see, right, x1 squared plus x2 squared will be positive everywhere, it will be 0 at 0 and then after that it will increase. So, you can think of all very easy ways of characterizing x1 squared plus x2 squared, right. So, if you say x1 squared plus x2 squared is a constant, you know what you will get, right. You will get a circle, everything is easy to characterize when you do not have the cross term. When you have the cross term, things become complicated. Okay. So, one of the goals that people do is, can you do a change of variables, some linear change of variables to eliminate the x1, x2. Okay. So, that is sort of like diagonalization, right. You can see how that is similar to diagonalization. If this were diagonal, if the matrix were diagonal, you will only have the square terms, you will not have the cross terms. So, you have a symmetric matrix, you want to make it diagonal, you can do a change of variable. So, this is where everything comes together, what we have been studying with symmetric matrices and diagonalization and quadratic forms and simplifying them by eliminating the cross variables. Okay. So, here is a change of variables. This is sort of inspired by the diagonalization, but if I did not tell you that, it will look like magic. If you say x1 is s1 plus s2, x2 is s1 minus s2, you see the cross term disappears. Okay, it will disappear and you will get a 10 s1 squared minus 6 x2 s2 squared. So, the question of course is, how does the above generalize, and the generalization is through the real spectral theorem and diagonalization. Okay. So, you can sort of expect that, and that is what will happen. Okay. So, this is how you use the spectral theorem to simplify quadratic forms. Supposing somebody gives you an arbitrary n by n real symmetric matrix, it has off diagonal elements. So, the quadratic so the quadratic form has cross terms, xi, xj terms, quite a few of them. Okay. So, you start with your orthonormal eigenvector basis. Maybe you write coordinates for these basis vectors with respect to the standard basis, right. So, we will always think of it like that. And we know aei is lambda I ei. So, these lambda i's are your eigenvalues, right, for this real symmetric matrix. Okay. So, now I can make a matrix S, which is E1 to En written in columns. Okay. Then I know S inverse, because this is an orthonormal basis vectors. So, S inverse will be the same as S transpose, right. We discussed this before. So, if you look at S transpose, you multiply S transpose S inverse, you can quite immediately see that only the diagonal entries will be 1, everything else will be 0 because of the orthonormal property. Okay. So, this A itself can be quite easily written as S D S transpose, okay, in the using this orthonormal basis decomposition, and D becomes lambda 1 to lambda n on the diagonal. Okay. I hope this is clear. I hope I have got the ordering of S and S transpose wrong. I always get mixed up on this. Maybe it is is it S transpose ds or S ds transpose, one of the two, okay. So, it does not matter what it is, it sort of works, okay. So, this is the diagonalization. The diagonalization is important. Of course, it matters, the sequence matters, but I mean the idea is basically the diagonalization, okay. Alright, so once you have a diagonalization like this with a suitable S, S ds transpose, then your X transpose Ax becomes X transpose. Instead of A, I will put S ds transpose, okay. Once I put S ds transpose here, I would get this, and then I can define an S which is S transpose X, and then what will happen to X transpose S? That will be S transpose, okay. So, my X transpose Ax becomes S transpose ds, and D is diagonal, okay. And once D becomes diagonal, I know that this X transpose Ax is simply lambda 1 S1 squared plus so on till lambda n Sn squared. There are no cross terms in this form, okay, once I get to the diagonalization, okay. So, the change of variables that takes you from X transpose Ax gets the change of variables that gets rid of all the cross terms in your quadratic form is strongly connected to the diagonalization and the spectral theorem like we studied for symmetric operators, okay. So, you might say what if A is non-symmetric, all this does not go, but you remember how I showed you that any quadratic form can be written as X transpose Ax where A is symmetric, right. So, it is possible to do that. So, symmetry is good enough, and this is a very nice way to get to the answer, okay. So, you see that quadratic form simplification has some very nice connections to real spectral theorem, okay. So, let us move on. The next very interesting question with respect to quadratic forms is what is called constrained minimization and maximization of quadratic forms, okay. So, okay, we have simplified X transpose Ax, we know how to simplify it. Can we put the simplification to some use, okay. In particular, can we find what is the maximum possible value for the quadratic form or the minimum possible value for the quadratic form with some constraint on X, okay. Now, that is the sort of problem I have defined here. I want to maximize over X, X transpose Ax with the constraint that norm of X should be 1, okay. The same thing with minimization. So, these are very interesting problems. They have a lot of applications. They show up quite often in practice, okay. So, it is good to do it, but why is this constraint? What if you do not put this constraint, you might ask. If you do not put the constraint, usually you will get 0 or infinity, okay. So, it depends on A, whether it is negative, non-negative and all that. But so if you do not constrain, you can quite easily solve this problem. So, it is not a big deal. If you do not constrain, you can just drive it to infinity. You can take some examples and see that it is easy to drive it to infinity, minus infinity, or it may be 0, okay. So, it is easy to do this if there is no constraint. So, when there is constraint, it becomes more interesting, okay. So, another way to view this problem, if you do not like this constraint, if you want to think of some other version of this problem, is to look at this problem. You max over all X, X transpose Ax by X transpose X. Now, X transpose X is just mod X squared, right. So, you can push that into the X and the X here. So it's both of these are equivalent, okay. So, there is no, it is not difficult to see that both these are equivalent. In case you are worried about it, you can do this. You can see X transpose Ax by norm X squared, norm X into norm X, right. And that is the same as I can write X transpose by norm X, okay, sort of, you hope you understand the notation, X by norm X, okay. So, this guy is the same as something with unit norm. So, this whole thing has unit norm, right. So, whether you are maximizing over all X or you are maximizing just X transpose Ax with the norm being 1, it is the same thing, okay. So, this problem is also equivalent. So, this is something nice. So, this sort of tells you the effect of A on the X transpose X, okay. You have a norm of X, what A does to the quadratic form when compared to the norm of X. If X is very large, what does it do? So, this ratio is meaningful in so many different ways. Okay, here is a very simple classic example. You might have solved this problem in so many other ways before, or you might be familiar with this. Max of 4xy. 4xy is clearly a quadratic form over x squared plus y squared equals 1. Okay, so this is the constraint that norm of x is 1. What is 4xy? This has a very simple interpretation of being a rectangle of largest area inscribed within a circle. Think about why that is true. You put a circle, x squared plus y squared is 1, describes the circle. Any xy that you pick on the circle, minus x minus y minus xy, x minus y, right? That is the rectangle. That area is 2x times 2y, which is 4xy. So you maximize 4xy over x squared plus y squared is 1. So this gives you that. There are various methods to solve it, and in this case it's not very hard, right? You can change it to one variable, right? You can make y as root of 1 minus x squared, and then you will get 4x root of 1 minus x squared, and then after that it's only a single variable maximization problem. You can differentiate equate to 0, you can do such things. So it's possible to do all that here using calculus. Okay? There are various other methods also, geometric, etc., that you can use. Okay? But the question here is how to generalize, right? How do I take this problem and then sort of generalize it to n dimension? You know, any quadratic form with this constraint, how do you solve it? Okay, n dimensions arbitrary a. Okay. Quick thing I want to point out here, you can also check that without any constraint, if supposing I don't put x squared plus y squared equals 1, if I only want to max 4xy, you know what's going to happen, right? You can go to minus infinity, plus infinity quite easily by choosing large and large and large values for x and y, okay, or positive, negative like that, right? So you pick it carefully, so you can drive it anywhere you like. So max and min without the constraint for quadratic forms is not so interesting. With the constraint, it becomes very interesting, okay. So anyway, so that sort of motivates the problem for you, and the real spectral theorem or the spectral theorem has a wonderful application in this context. We'll see some quick applications, and you'll see how easily it solves the problem, and also getting rid of the cross terms is also very important here. Okay, so you'll see all that plays a role. Okay, so here is how the spectral theorem is involved. We have the n by n real symmetric matrix, and associated with that matrix is the orthonormal eigenvector basis. Again, think of this E1 to En in terms of coordinates with respect to the standard basis. That's a easy way to write things down. It helps us to write things down very easily. So now once I know that, I know the spectral theorem tells me A can be written as lambda 1 E1 E1 transpose plus so on till, I forgot the lambda n there. Okay, so the lambda n should come there, En transpose, and this lambda 1s I will pick like this. Okay, so I will pick lambda 1 to be my largest eigenvalue, then lambda 2, then lambda 3, so on till lambda n. Okay, so lambda 1 is the largest eigenvalue of A. Okay, lambda n is the smallest eigenvalue of A. It could be positive, negative, whatever, I don't care, but I know it's real, right? All eigenvalues for A are real because it's symmetric, and then lambda 1 is the largest eigenvalue, lambda n is the smallest eigenvalue. Okay, so this is how it goes. Okay, so this is A, this lambda n I've forgotten here, it's a typo, you should put it there. Okay, so now let's see how this can be used. Okay, now in a quadratic form, right, x transpose Ax, I'm going to think of x, right. So this is same as what we did with the diagonalization. I'm just describing it a bit differently, but this description helps you in the maximization more directly, I think. Okay, so you express x in terms of the orthonormal basis E1 to En. Okay, so x1 is its coordinate of E1, xn is its coordinate of x which multiplies En, right. So x becomes x1 E1 plus so on till xn En. Right. So you basically express x as a linear combination of E1 to En. I know this is always possible because this is a basis, and you get x1 to xn. So clearly norm x squared is x1 squared plus xn squared. Is that okay? So why is this important? So because I'm going to constrain my norm to be 1. Okay. So this x1 squared plus xn squared have to sum up to 1. Okay. So this is something that has to happen. So now what is x transpose Ax? Okay. You put A in this form and x in this form, and you just substitute x transpose Ax and simplify, you know what's going to happen, right? All the cross terms will disappear. You will get lambda 1 x1 squared plus so on till lambda n xn squared. Okay. So now this is our problem. Okay. So I want to maximize this or minimize this. Okay. Let's look at maximizing this with the constraint that this is equal to 1. Okay. And what do I know? I know this guy. Okay, this is very important. Okay, lambda 1 is the largest. Okay, so if I want to maximize this, what should I do? I should make sure that whatever multiplies lambda 1 is as large as possible, right? Right, that would give me the maximum value for this summation, because there is nothing else, that's confusing this. It's every term is just x1 squared, xn squared, right? It's all positive. Every term contributes in some sense positive, and then the lambda gets multiplied by a positive number only, right? So lambda 1 is getting multiplied by x1 squared, which is positive. So if I want to maximize this sum, I want to make sure that x1 is as large as possible, right? Now suppose I don't put any constraint on x, I can make x1 infinity or something very large, and then just simply the sign of lambda 1 will sort of dominate what happens, whether in maximization or minimization. Let's say lambda 1 is positive, right? So then if you want to maximize, you simply let x1 become larger and larger and larger, you will get plus infinity, right? So that's what will happen, okay? But we have this constraint that the sum squared of x1 to xn has to be equal to 1. So what is the largest possible value that x1 can take? That is 1. Right, largest, so we want to set x1 as large as possible to maximize, right? Okay, so that's the main story, and given the constraint, okay, since norm x is constrained to be 1, largest x1 equals 1. Okay, so you cannot go above 1. Okay, so the largest x1 you can put is x1 equal to 1, and once x1 becomes 1, what happens to x2 to xn? All of them become 0. Okay, so this corresponds to x1 equals 1, and that implies x2 equals xn equals 0, and that implies x equals e1, isn't it? So if you put x1 as 1, everything else is 0, x becomes e1. So to maximize x transpose Ax under the constraint norm x equals 1, you simply have to pick x equals e1, and the maximum value will be equal to lambda 1. It cannot go above that. Okay? So that's a very simple result that you get once you get this form. If you did not have this form, if you had x1, x2, x1, x3 and all, you can't make these easy calculations. Okay? So notice how the spectral theorem is playing a huge role here. Okay? So the constraint maximum for norm x equals 1 x transpose Ax is simply lambda 1, and it's achieved at x equals e1. That's it. Okay? How simple is it to solve this using the spectral theorem, right? So there's no calculus, there's no differentiation, there is no nothing more is involved. Just the answer comes out very cleanly using the spectral theorem. Okay? The same thing can be very easily done for the constraint minimum, right? Supposing you want to minimize, what should you do? Right, I want to make xn as large as possible, right? Anything else I do will only increase my quadratic form's value, right? Xn should be as large as possible, so you pick x equals en, so xn is 1, everything else is 0, and the minimum becomes lambda n. Okay, so maximizing and minimizing quadratic forms with the constraint is quite easy, and that simply is directly connected to the maximum eigenvalue of A and minimum eigenvalue of A, and achieved at the corresponding eigenvectors. Okay, the maximum, the eigenvector corresponding to the maximum value, or the eigenvector corresponding to the minimum value. Okay, simple enough, right? So we can further constrain the problem. So let's say I am not interested in the maximum eigenvalue, right? So I don't care so much so about the maximum eigenvalue. I want to make sure that I am not anyway related to the maximum eigenvalue. Okay, so you may have a problem like that. Okay, so in this basic problem, I may want to put an additional constraint saying the inner product of x with e1 has to be 0. Okay, so I don't want anything to do with the maximum eigenvector. I don't want to be anywhere near there, but I want to maximize the quadratic form given the constraint that norm x is 1, but inner product x comma e1 should be 0. Okay, even these kind of problems are easy enough to do, right? So if you just think about this problem, just fundamentally, you have maximization of a quadratic form, degree 2, right, x1, x2. What are the constraints? There is a degree 2 constraint and a degree 1 constraint. Okay, so it's sort of complicated from a pure calculus point of view if you think of it as an optimization problem, but because of the special properties of quadratic forms and because of the spectral theorem, even these kind of problems have a very simple solution. What do? If I know x comma e1 is 0, then I know x has to have this form, right? X has to belong like this, the e1 is 0, everything else is could be non-zero, and norm x will simply be x2 squared plus xn squared, and x transpose Ax is this, right? And what is the maximum among this? Lambda 2. Okay, so the constraint optimization is quite easy to do. You see that it's lambda 2 and it's achieved at x equals e2. That's it. Okay, so these are all easy and nice results that one can get using the spectral theorem when you are maximizing with some constraint, when you are maximizing the quadratic forms. Okay, so we have seen simplifying quadratic forms and maximizing quadratic forms. Spectral theorem simplifies matters tremendously. So you can do this in general for any size, right? So that's the power of this. So there is an analogous way to think of complex also, and self-adjoint matrices and all that. The same thing goes through. There is no problem there, except that you have to write it in a bit more complicated language. So I've chosen this simple one for description. Okay. All right. The next couple of things I want to point out, I'll go through a bit faster, and these are not slightly advanced ideas, not so important, but I want to point out how easy it is to use the ideas we have discussed to quickly provide definitions at least, and give you some motivation for why these are interesting from a theoretical point of view. Okay. Supposing I have an M cross N matrix, people associate a norm with the matrix. Okay. So far we've been thinking of norm with vectors. You can also associate a norm with operators. Okay, so A of course represents an operator. I'm thinking of it in the matrix representation. Think of it as the operator only if you want. So the norm of A, denoted norm A, you define it like this. It's a max over all AX, norm of AX, such that norm X equals 1. Okay, so there is a good motivation for why this is defined this way. Okay, so you look at all X which have norm 1 and look at how much A increases that norm, right? Ax is a vector, right? But remember, Ax is a vector in Fm, right? X is a vector in N. Okay, so but still, it's a vector. So if you start with norm 1 vectors, how much does A increase norm by? Okay, so it's sort of like a reasonable thing to know, right? If you have an operator, you want to know how much amplification it's doing to norm, right? So that represents the norm of the operator. Okay, X as a norm, Ax as a norm. What is the norm of A? It's the maximum amplification it can do to norm. Okay, so there is a sense in which this works out. Just like we looked at before, norm A, instead of doing the constraint of x equals 1, you can say max over all x norm Ax by norm x. Okay, so it's the same thing because it's linear. You can push this x inside, so you have norm of. You can think about why this is well defined. So this is going to work out, and this is correct. Okay, so this and this are the same. So in this sense, norm of A represents the maximum amplification that X will get from A. Okay, so that's the norm. Okay, that's good to know. So maximum increase, but this is maximum multiplicative increase, sort of maximum amplification. Okay, so there's another way to write this. People write this also differently. So this implies norm AX is less than or equal to norm A times norm X. Okay, if you know what norm A is, norm A plays this kind of a role. Okay, so quite often you want to know, after operating with A, how bad can my norm be, how big can my norm be. That gets bounded by norm A into norm X. Okay, so that's why this is very interesting in practice. One might also want to look at the minimum. Okay, even though we don't look at that too much. From the norm, the minimum doesn't play a role, but the minimum in practice can also play a role. How much will A, what is the opposite of amplification, whatever that is, how much A reduces the norm of X. Okay, so that also might be interesting from some point of view. Okay, anyway, this is norm. I don't want to go too much into why norms are useful, but you can see that this is well defined, and one can look at how to operate with it. Okay, once again, the spectral theorem comes to our rescue in characterizing norms in terms of eigenvalues and eigenvectors. But remember, A is M cross N. Where will eigenvalues come from? Okay, so notice how they enter the picture here. So there is a connection between matrix norm, quadratic forms, and all we've been studying. So for that, you just look at norm squared, right? So norm squared is going to be max norm Ax squared. Okay, so once you go to Ax squared, I can write in terms of inner product, right? Norm Ax squared is inner product Ax comma Ax. Now what is inner product Ax comma Ax? It's X transpose A transpose Ax, isn't it? Okay, so it's quite easy to see why this is true. So this is nothing but a quadratic form defined by A transpose A. Notice A transpose A is symmetric. It's in fact even positive. Okay, so we can come to that later. We know it's operator joint product, right? So it's a positive operator. It's a symmetric definitely. So this X transpose Ax is a quadratic form now. So this problem of computing norm for an operator is actually the same as constraint maximization of a quadratic form. Okay, so all these problems are sort of similar, and they all defined from the same sort of assumption, and they all tie up into the eigenvalue of symmetric operators. Okay, so it's all very interesting how these things show up. So that's something to keep in mind. So while we define norm as some maximum amplification that's produced by an operator on the vector x, it is the same as the maximum quadratic quadratic form that can take with the constraint And the quadratic form is defined by A transpose A. Even though A is M cross N, A transpose A is going to become N cross N or something like that. Okay, so you get something very reasonable here. Okay, so let's say the largest eigenvalue of A transpose A is lambda max of A transpose A, and that's going to be non-negative, right? So because it's a positive operator, all its eigenvalues are non-negative, so it's going to be greater than or equal to 0. Okay, so from this we know what is the largest constrained maximization of X transpose AX. It is simply lambda max of A transpose A. So this gives you a very succinct, clean formula for the norm of any operator A. The norm of any operator A is square root of lambda max of A transpose A. Okay, so it's very clean, nice relationship for the norm of A, and once again you can see the spectral theorem and positive operators and all of these things play a role here. Okay, so that's all I want to say about matrix norm, and maybe if you take some advanced courses in linear algebra, you would study more about matrix norms and its applications in general. Okay, so the last thing I want to point out in this lecture is basically an application of positive operators in optimization. Okay, so this shows up when you look at smooth multivariate functions, arbitrary functions. Let's say some function f of x1 to xn, each xi is a real variable, let's say, but f is smooth. What do I mean by smooth? I'll assume it has continuous single and double partial derivatives. You know what partial derivatives are, right? Partial derivative of f with x1 or x2 or so on, and also double derivatives. You can take a partial derivative twice, say with respect to x1, or once with respect to some xi and another time with respect to some other xj. Okay, so all these are continuous, we will assume. So you have relationships like this being true, right? The partial derivative, if you do in any order, they will be equal, right? So when you're smooth, you can make all these assumptions. Okay, all these are true, bounded, everything you can assume if you want. So basically smooth, nice functions like this, when you want to optimize them. So optimize meaning you want to find, so now you have to sort of imagine in your head. So you have all this, think of 3 dimensions or 4 dimensions or something. All these x1 to xn are living in this big space. At every point I've defined a function for you. Okay, and this function is going to go up in some ways, come down in some way. If you're in any point x1 to xn, you can go in so many different directions, and in every different direction this function may increase or decrease or behave in various ways. Okay, now I want to optimize this function. So I want to find a point where this function, wherever we go, it's only going to go down. It's like a hill, hilltop, right? So you want to find maximum value or minimum value. Okay, bottom of a valley, so to speak, right? So you come somewhere, and then whichever direction you go, you can only go up, right? So I want to find those kind of points, local minima, local maxima, they are called, for multivariate function. And this is the heart of all optimization problems. Many engineering problems, wherever you do, ultimately you will end up with one big function of several variables, and you want to find local maxima, local minima, understand this function, understand the landscape of this function, how does it look from different points of view. So this is a crucial thing in all engineering applications. Okay, so what is the connection between this and linear algebra and positive operators? Here is the connection. Okay, so we won't prove this result, it's way beyond the scope of this class. I'll just point it out, and later on if you take a course in optimization, you'll study more about this. The first thing is, there is this notion of critical points for such functions. What are the critical points? The points at which all partial derivatives vanish. Okay, so the derivative with respect to one variable is sort of tells you how the function behaves if you move in that direction, right? So if my derivative goes to 0, it means that function is not really changing that much in that direction. Okay, neither increasing nor decreasing, right? So that's sort of what this means. It's sort of flat in that direction. Now if all partial derivatives are 0, in all directions it has that behavior. Okay, so you expect something to happen there, right? In all directions I'm not seeing any increase or decrease, right? So that should correspond to a local minimum, local maximum, or it could also correspond to something called a saddle point. Okay, so the saddle point is a little bit more complicated, as in local maximum means everywhere it decreases, right? Local minimum means in every direction you go it only increases, but saddle point, in some directions it may increase, some directions it may decrease. Okay, so it's sort of it's a little bit more than a general point. You might say, okay, saddle point, what is the difference between a general point and a saddle point? Saddle point is a critical point, as in the partial derivatives vanish. Okay, so it's sort of flattish, but in some directions it will go flatten up, in some other directions it will go flatten down. Okay, so that's why you can imagine the saddle on a horse, right? If you think of a horse back and there's a saddle, in some directions you go down, some directions you go up, right? So that's the saddle point. It's still critical, as in the partial derivatives vanish. In general points, the partial derivatives may not vanish, so there's no flat behavior in the neighborhood, but it's not a maximum or a minimum. Okay, so this classifying critical points into maximum, minimum, and saddle point is very important. You need to get a sense in your function of multiple variables how it behaves in different points. Okay, and once again, linear algebra comes to your rescue through this notion of a Hessian matrix. Okay, this is the Hessian matrix. It's basically you collect all the possible partial derivatives and put them together in a matrix, right? So for every xi and xj, you have a double partial derivative. Okay, you might be x1 squared, you put it on the diagonal. If it's xi xj, you put it in the ijth element. Xj xi will be in the jith element. Okay, because of these continuous assumptions, okay, it's very reasonable to expect the Hessian to be symmetric. Okay, for most functions, you will get a symmetric Hessian. Okay, so this symmetric operator or matrix, at every point you can evaluate it, right? Of course, in the critical points also you can evaluate it. Okay, so all this is sort of similar to your double derivative method for detecting local maxima minima, right? Functions of one variable, you might have heard, you take a first derivative, if it's equal to 0, you get critical points. And how do you find whether it's maxima or minima? You take the double derivative, okay, and check its sign. If the double derivative is positive, it's a minima, double derivative is negative, it's a maxima. So sort of like that. This is the extension or generalization of that to n dimensions, and a positivity of the symmetric operator now will play a role. Okay, in one dimension it was just positivity or negativity of the double derivative at the critical point. Here you have to look at the Hessian at the critical point. It will be a symmetric operator. You have to check whether it's positive or not. Okay, the result, which is true, we won't prove this, is that a local maximum at the critical point if Hessian is negative definite, a local minimum at a critical point if Hessian is positive definite at that point, and if it's neither positive nor negative, it can also happen, right? All operators need not be positive, negative definite or negative definite, then you get a saddle point. Okay, so this is a nice characterization, and this is how positive operators, a notion of positivity in operators is used in optimization. And if you take further courses in optimization, you will see such ideas explored in great detail. Maybe you will see a proof for this result, right? So you will see all that. Okay, that's the end of this lecture. Hopefully this lecture gave you a sense of how these spectral theorems are not just idle theoretical results. These characterizations are very powerful. They're powerful in optimization of simple things in some sense like quadratic forms, and even more complicated arbitrary functions, as long as they are smooth in some way. Okay, thank you very much.